We've been talking about Newton's first law of motion that states, in order to accelerate an object, a net external force must be applied to that object. So, if we wanted to accelerate a nail downward into a block of wood, we would need a hammer to apply a downward net force. If we were to do this, you would find that the hammer seems like it bounces upwards as the nail is driven downwards. Why would it do that? Well, it's the same reason why, if you were to punch a wall, both the wall and your hand would feel the punch. See, the genius of Sir Isaac Newton doesn't just stop at understanding a net external force causes an acceleration. Newton also understood that such an isolated force, such as the applied force of the hammer onto the nail, cannot exist. He understood that all forces come in pairs. Such is Newton's third law of motion. The most common rendition of this law states, for every action, there is an equal and opposite reaction. What that truly means is if two objects, let's call them object 1 and 2, interact, then the force that object 1 exerts on object 2 is equal and opposite to the force that object 2 exerts on object 1. We can write this mathematically as F sub 1 on 2 is equal to negative F sub 2 on 1. So when the hammer applies a force to the nail downwards, the nail applies an equal force to the hammer in the opposite direction, upwards. We can write this as F sub hammer on nail is equal to negative F sub nail on hammer. Remember, force is a vector, so the negative indicates the direction of the force. This law holds true for every single force. When you punch a wall, you exert a force on the wall, and as a result, the wall exerts a force onto you of equal and opposite magnitude. That explains why your hand would hurt. And we can write this as F sub hand on wall is equal to negative F sub wall on hand. This pairing of forces is what we call an action and reaction force pair. When we think about the action and reaction force pair, it's natural for us to think of the force of your hand on the wall as the action and the force of the wall on your hand as the reaction. Because from your perspective, it's as if you started the interaction. Reality is that the action and reaction forces happen at exactly the same time. The wall hits you at exactly the same time as you hit the wall. And by that reason, either force can be labeled as the action or reaction force. Now, don't be fooled by the deceiving simplicity of this law. It is a fundamental principle that's really responsible for everything that we do. Let's consider a bug crashing into the windshield of a moving car. We know that the bug experiences a force exerted by the windshield when it collides with the windshield. According to Newton's third law, that means the windshield experiences a force of equal magnitude exerted by the bug in the opposite direction. That means as the windshield pushes the bug leftward, the bug pushes the windshield rightward. Let's think about that for a moment. If the bug and the windshield experience a force, both objects would also experience an acceleration. In fact, you can imagine that the bug accelerates to zero velocity upon crashing into the windshield. So, how come the car's velocity appears unchanged? Well, that's because of the car's inertia. The car is so much more massive that it has so much more resistance to changes in its motion, that it doesn't accelerate nearly as much as the bug, even though it experienced the same magnitude of force as the bug. So be careful. Just because the result, acceleration, of the forces are unequal does not mean that the forces themselves are unequal. Let's now consider a lemon at rest on a table. While it's on the table, it experiences two forces, the gravitational force from the earth and the normal force from the table. Each of these two interactions have their own action-reaction force pair. For the force of gravity between the lemon and the earth pulls the lemon downwards with the same magnitude of force as the lemon pulls the earth upwards. For the normal force between the lemon and the table pushes the lemon upwards with the same magnitude of force as the lemon pushes the table downwards. Herein lies another common misconception of Newton's third law. We're not talking about balanced forces acting on an object, such as the gravitational force and the normal force on a resting object. No, we're talking about each force having its own reaction force. The gravitational force has its own action-reaction pair, and the normal force has its own action-reaction pair. And for each interaction between two objects, the action force involves the same two objects as the reaction force. So, if we were to diagram the gravitational force, when the earth pulls the lemon downwards, we would draw this downward force on the lemon because it's the lemon that experiences the pull. And when the lemon pulls the earth upwards, we would diagram this upward force on the earth because this time it's the earth that experiences the pull. Similarly, if we were to diagram the normal force, when the table pushes the lemon upwards, we would draw this upward force on the lemon because it's the lemon that experiences this push. However, when the lemon pushes the table downwards, we would draw this downward force on the table because this time it's the table that experiences the push. You'll notice that we're drawing the action and reaction forces on separate objects. Action and reaction pairs will never appear on a single free body diagram because a single free body diagram only conveys the forces on that one object. Newton's third law explains the forces two objects experience as a result of each other. This law is built into everything we do. We wouldn't be able to launch rockets into space without Newton's third law. In fact, we wouldn't be able to drive or even walk. As a rocket ejects hot gas downwards, the gas reacts to propel the rocket upwards. As the wheels of your car push the road backwards, the road reacts to push your wheels and the car forward. And similar to all of that, as your feet push on the ground backwards, the ground reacts to push you and your feet forward. I'm telling you, you can't escape Newton's third law. Every single force can be described by its action force and reaction force. The action can be described as the force one object exerts on a second object, and the reaction force can be described as the second object exerting an equal and opposite force on the first object. And this action and reaction force are always equal in magnitude, always opposite in direction, and always involve the same two objects. Newton's third law does well to explain a number of our experiences and interactions. It even explains why external forces are required to accelerate an object. If you weren't already sitting in your chair watching this video, find a chair and take a seat. Now let's say there's a bag of flaming hot Cheetos behind you that you can't quite reach. You don't really want to stand up and go get it because you just sat down. So, how would you move yourself and the chair to reach it? Yeah, not too difficult, right? You probably just use your hands to push off against the table. Okay, let's try this again, but this time, don't use your hands. This isn't really that challenging. You probably used your feet and pushed off the floor. Fine. This time, see if you can move you and your chair horizontally across the room without either you or the chair touching anything else. The best you're going to get is probably tipping yourself over. Why is this so difficult? It doesn't have anything to do with any property the chair or you possess. It's actually plainly impossible for you to make this happen. You can't move yourself and the chair without an external force, and you can't experience an external force without interacting with another object. Let's explain this using Newton's third law. No matter what strategy you used to attempt to move yourself in the chair, you applied a force onto the chair, and as a reaction, the chair applied an equal and opposite force onto you. So if you tried pushing the back of your chair to the left, the back of the chair would push you to the right with equal strength. So when we look at the total force acting on you and the chair, these would simply add to 0. A 0 net force results in a 0 net acceleration. This is no different from trying to get your van to move across the road just pushing it from the inside. Every push you exert onto the car has an equal and opposite reaction force that the car exerts onto you. It doesn't matter how hard you push or in what direction you push, because the van pushes back on you the same amount. And in total, you and the van experience no net force and therefore cannot accelerate. And that is why Newton's first law stipulates that an external and not an internal force is required to accelerate an object. In fact, this action and reaction law is so fundamental, it doesn't just explain Newton's first law. It also explains a lot of other major laws in our universe, including the conservation of energy and the conservation of momentum. But that's for another day. Next time, we'll take a look at Newton's second law as it describes the mathematical relationships among force, inertia, and acceleration. See you later on Penguin Physics.